Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. So, in the previous modules we have looked at SVD or singular value decomposition based MIMO wireless transmission. We have looked at how the singular value decomposition, that is, first what is the singular value decomposition, how it can be applied in the context of MIMO transmission, that is the post processing at the receiver, the pre-coding at the transmitter, the spatial multiplexing or the decoupled spatial channels, and finally the optimal power allocation across the various sub channels to maximize the sum rate or achieve the Shannon capacity of the MIMO wireless channel. Now, to better understand all these aspects, let us look at a simple example which will summarize these aspects related to SVD or singular value decomposition based MIMO channel. So, today we are going to look at SVD based MIMO transmission, but we are going to consider a simple example to help understand these aspects comprehensively. Okay. So, for this consider a 3 cross 3 So, let us say we have a 3 cross 3 MIMO channel, that is the MIMO channel matrix is H, which is given as 2 minus 6 0 3 4 0 0 0 2. So, this is a 3 cross 3 MIMO channel, which means that basically my R is equal to T 3, my T is equal to 3, that is number of receive antennas is equal to 3, number of transmit antennas is equal to 3, my channel matrix H is this 3 cross 3 channel matrix. Now, let us denote these columns by C1 bar, C2 bar, C3 bar. Now, you can see that in this MIMO channel matrix, in this 3 cross 3 MIMO channel matrix which has 3 columns C1 bar, C2 bar, C3 bar, these 3 columns are orthogonal. So, you can see that if I take any 2 columns out of these 3 columns, if I take any 2 columns, I will have C1 bar Hermitian, Ci bar Hermitian. So, if I take any 2 columns, I will have Ci bar Hermitian, Cj bar equal to 0, that is the columns are orthogonal on this matrix, the columns are orthogonal. For instance, let us look at C1 bar and C2 bar. I have C1 bar, that is the first column equals 2 3 0, C2 bar, that is the second column equals minus 6 4 0. So, if I look at C1 bar Hermitian C2 bar, that is equal to the row vector 2 3 0 times the column vector minus 6 4 0, and this is equal to 2 into minus 6 minus 12 plus 3 into 4 12 plus 0 into 0 0, which is equal to 0. So, C1 bar and C2 bar are orthogonal. Similarly, you can verify this for the other columns, that is you can see C2 bar and C3 bar are orthogonal, that is C2 bar Hermitian C3 bar is 0. Similarly, C1 bar Hermitian C3 bar is 0, that is C1 bar and C3 bar orthogonal. So, all the columns of this 3 cross 3 channel matrix are orthogonal. How do we do the singular value decomposition? I am going to illustrate now how to perform the singular value decomposition. Let us look at, so the SVD can be found as follows. Let us go back to our channel matrix, which is 2 minus 6 0 3 4 0 0 0 2. So, let us look at this channel matrix. Now, you can see I can normalize each column, I can make each column unit norm, I can normalize each column, that is I can make each column as unit norm. Therefore, I will have H equals the first column divided by the norm of the first column. The norm of the first column is square root of 2 square plus 3 square plus 0 square, that is square root of 4 plus 9, that is 13. So, divide by the square root of 13. So, I have 2 divided by 13, 3 divided by 13, 0 divided by 13, which is 0. Similarly, the second column is minus 6, 4, 0. The norm of this second column is square root of 6 square plus 4 square plus 0 square, that is square root of 36 plus 16, that is square root of 52. So, I can divide by the square root of 52 to normalize this column or make this column unit norm. So, I will have minus 6 divided by square root of 52, 4 divided by square root of 52, 0 divided by square root of 52 is 0, and the third column has only one element 2. So, the norm of this is square root of 2 square, which is square root of 4, which is 2. So, I have 2 divided by 2, which is 1. And now, since we are dividing by the norms, I have to multiply each column by the corresponding norm. So, I have square root of 13, square root of 52, 2 comma 2. Okay. So, this is the diagonal, this is the diagonal matrix. Now, if you look at this matrix, if you look at this first matrix, call this U. Now, you can see that U Hermitian U will be identity, because it has now orthogonal columns and we have normalized each column to have unit norm. Therefore, U Hermitian U will be identity. However, if you look at this matrix, the singular values, that is square root of 13, square root of 52 and 2 are not ordered, because square root of 13 is less than square root of 52. I have to arrange the singular values in a decreasing order. Therefore, I need square root of 50. So, I need the first singular value as square root of 52, the second singular value as square root of 13, the third singular value of as 2. Therefore, now we have to order the singular values. So, here the problem is that the singular values are not ordered or not in decreasing order, or not in the singular values are not in a decreasing order. Therefore, I can rewrite this now as, so let me write this once more. I have 2 divided by square root of 13, 3 divided by square root of 13, 0, minus 6 divided by square root of 52, 4 divided by square root of 52, 0, 0, 0, 1 times I have square root of 32, 0, 0, 0, square root of 52, 0, 0, 0, 2. What I am going to do now? I am going to switch the first 2 columns of this first matrix U. So, that will give me minus 6 by square root of 52, 4 divided by square root of 52, 0, 2 divided by square root of 13, 3 divided by square root of 13, 0, 0, 0, 1. Now, since I am switching the first 2 columns of the first matrix, I have to switch the first 2 rows of the second matrix. So, I will have 0 square root of 52, 0 square root of 13, 0, 0, 0, 0, 2. So, this is what I have. Now, I want to again shift the columns to make the second matrix a diagonal matrix. I want to swap columns 1 and 2, which means I can write this as the following thing: 6 minus 6 divided by square root of 52, 4 divided by square root of 52, 0, 2 divided by square root of 13, 3 divided by square root of 13, 0, 0, 0, 1 times. Now, let me make this a diagonal matrix square root of 52, square root of 13, 2, 0, 0, 0, 0, 0, 0, and now I can multiply this by the matrix which is 0, 1, 0, 1, 0, 0, 0, 0, 1, and now you can see this will swap the columns of the diagonal matrix. So, now you can see I have my matrix U, I have my diagonal matrix sigma which has the non-negative singular values in decreasing order, I have my matrix V Hermitian, and now if you can verify this, you can verify this, the matrices U, sigma and V satisfy the properties. The matrices U, sigma V, I have U Hermitian U is identity, I have V Hermitian V equals V V Hermitian equals identity, I have sigma as the diagonal matrix square root of 52, square root of 13, 2. So, sigma is a diagonal matrix with singular values sigma 1 equals square root of 52, sigma 2 equals square root of 13, sigma 3 equals 2. Therefore, all the singular values sigma 1, sigma 2, sigma 3 are greater than 0. So, the singular values are positive. Further, we have sigma 1 greater than sigma 2 greater than sigma 3, which means the singular values are in decreasing in decreasing order. So, we have the diagonal matrix sigma, the 3 singular values square root of 52, square root of 13 and 2 which are non-negative, in fact they are positive, and these singular values are in decreasing order because square root of 52 is greater than square root of 13 is greater than 2. So, this and together with the properties that U Hermitian U is identity, V Hermitian V equals V V Hermitian equals identity, this forms a valid singular value decomposition for the matrix H, that is the 3 cross 3 channel matrix H that has been described in the beginning of this SVD based MIMO transmission example. So, now let us proceed with the post processing and pre processing. So, now we have the matrices U sigma V Hermitian. As we said, at receiver we perform y tilde equals U Hermitian y bar, which is basically I have the structure of matrix U. So, U Hermitian is minus 6 by square root of 52, 4 divided by square root of 52, 0, 2 divided by square root of 13, 3 divided by square root of 13, 0 and 0, 0, 1 times y1, y2, y3, this is basically my y bar, this is basically my U Hermitian, and this is my y tilde, which is y1 tilde, y2 tilde, y3 tilde, which is basically my 3 cross 1 vector y tilde. So, at the receiver I am generating y tilde as U Hermitian times y bar, and since we know the matrix U which follows from the SVD of the channel matrix H, I can perform U Hermitian y bar to generate the vector y tilde. Now, let us look at the pre-processing at the transmitter. At the transmitter, At the transmitter I perform, remember I perform x bar equals V x tilde, that is this is also termed as, remember we also term this as, pre-coding. Therefore, I have x1, x2, x3 is equal to V, which is 0, 1, 0, 1, 0, 0, 0, 0, 1 times x1 tilde, x2 tilde, x3 tilde. So, this is basically my x bar, this is basically my matrix V, this is basically my matrix, my vector x tilde, and this is basically, this is the pre-processing at the transmitter. This is transmit, this step is also known as transmit pre-processing. This step is also known as transmit pre-processing or pre-coding. So, this step is also known as the transmit pre-processing step in SVD based MIMO transmission, or basically pre-coding. And now after this, what am I going to have at the receiver? As we have already seen this in the previous module, I am going to have y tilde equals sigma times x tilde plus w tilde. So, what I am going to have at the receiver is, I am going to have y tilde equals sigma times x tilde plus w tilde. Now, y tilde equals y1 tilde, y2 tilde, y3 tilde, which is equal to sigma, that is square root of 52, square root of 13, 2, 0, 0, 0, 0, 0, 0 times x1 tilde, x2 tilde, x3 tilde plus w1 tilde, w2 tilde, w3 tilde. And therefore, now if you can look at this, since sigma is diagonal across each sub channel, I have a decoupled, I have 3 decoupled channels in this MIMO wireless system. Namely, I can now separate these as y1 tilde equals square root of 52 times x1 tilde plus w1 tilde, y2 tilde equals square root of 13 x2 tilde plus w2 tilde, y3 tilde equals 2 times x3 tilde plus w3 tilde. So, what do I have as a result? I have 3 decoupled channels, and this is basically spatial this we said is spatial multiplexing. Why is this spatial multiplexing? Because now I am able to transmit 3 symbols. What are the 3 symbols? x1 tilde, x2 tilde, x3 tilde on the same frequency at the same time, right, because I am using the spatial dimension in the 3 cross 3 MIMO channel. I am using the 3 transmit and 3 receive antennas to simultaneously multiplex 3 symbols x1 tilde, x2 tilde, x3 tilde across the MIMO wireless channel. This is also known as spatial multiplexing. That is what we have seen in the previous module. This is known as spatial multiplexing. Okay. Now, let us look at optimal power allocation. In this optimal power allocation, that is, if the transmit power is P, optimal power allocation. Optimal power allocation for what? Optimal power allocation to maximize some rate that is which implies basically if I am maximizing the sum rate, this automatically implies to achieve capacity or Shannon capacity, to achieve the Shannon capacity, I have P1 equals 1 over lambda minus sigma square divided by sigma 1 square subscript plus, which is 1 over lambda minus sigma square divided by sigma 1 square equals 52, right. Remember, the plus sign indicates the quantity. If the quantity inside the brackets is greater than 0, and if it is equal to 0 if the quantity inside the brackets is less than or equal to 0. Okay. And similarly, P2 equals 1 by lambda minus sigma square by sigma 2 square superscript plus, which is 1 over lambda minus sigma square divided by 13 plus P3 equals 1 over lambda minus sigma square divided by sigma 3 square plus, which is 1 over lambda minus sigma square divided by 4 plus. Now, to complete this example, let us consider a noise power. Consider now noise power sigma square equals 0 dB, which implies 10 log 10 sigma square equals 0, which implies sigma square equals 10 to the power of 0 divided by 10, which is equal to 1. So, the noise power is 1. Let us consider P equals the total power, that is the total transmit power. Let the total transmit power be equal to 3 dB, which means 10 log to the base 10, P equals 3, which implies P equals 10 to the power 3 by 10, which is approximately equal to, 10 to the power of 0.3, which is approximately equal to 2, as we have seen several times. 3 dB equals 2. Therefore, we must have P1 plus P2 plus P3 equals 2, which means if I now substitute for P1, P2, P3, I have 1 minus 1 over lambda minus 1 by 52. Remember, P1 equals 1 over lambda minus sigma square by 52, but sigma square is 1, plus 1 over lambda minus sigma square by 13, but sigma square is 1, plus 1 over lambda minus sigma square by 4, but sigma square equals 1 equals the total power, which is 2. And now I can solve for 1 over lambda, implies 1 over lambda equals 2 plus 1 over 52 plus 1 over 13 plus 1 over 14 divided by 3 equals 0.7821. So, I am able to, so what I am doing? I am finding the power, each of the powers for optimal power allocation. The sum of the powers must be equal to the total transmit power, that is 3 dB or 2. From this equation, what am I finding? I am finding this quantity 1 over lambda, where lambda is the Lagrange multiplier of the optimization problem, remember that. So, I have found out 1 over lambda, and 1 over lambda is 0.7821. I do not need to find lambda, because really all I need is 1 over lambda to find each of the powers. Now, substituting this 1 over lambda, I can find each of the powers. So, power 1, so if I look at this, so power 1 is now 10 log to the base 10 1 over lambda minus sigma square divided by 52 equals 10 log to the base 10 0.7821 minus 1 over 52, which is equal to 1 minus 1.1755 dB. Similarly, P2 equals 10 log to the base 10 0.7821 minus 1 over 30 equals minus 1.517 dB. P3 equals 10 log 10 0.7821 minus 1 over 4 equals minus 2.74 dB. So, what we have done is we have found P1, we have found the expression for P1, we have found the power P2, we have found the power P3, and these are the powers. This is what are these P1, P2, P3 powers for optimal. These are the powers for optimal power. These are the powers for optimal power allocation. What we have said is these are the powers that maximize the sum rate of the MIMO wireless channel, or basically achieve the Shannon capacity of the MIMO wireless channel. And if you observe closely, you will also observe something interesting, that the power 1 is minus 1.17 dB, power 2 is minus 1.51 dB, power 3 is minus 2.74 dB. You will observe that the power is decreasing, power allocated decreases as the gain sigma I square of the that is what you will observe, is that you will observe interestingly, that is for various channels I, the channels I which have a higher gain, that is higher value of sigma I square, have a higher power. The channels which have a lower value of sigma I square, that is lower gain, have lower power. So, the power allocated in the optimal power allocation decreases as the gain of the channel progressively decreases, which means very interestingly you are allocating lesser power to poorer channels and you are allocating more power to stronger channels, and that helps you optimize the power allocation for MIMO wireless system towards maximizing the transmitted rate between the transmitter and receiver. We also said this algorithm is known as the water filling power allocation. The water filling power allocation basically states that in a vessel where the vessel height is high, the water level or the height of the water level is basically the net water level, which is basically the level of the water minus the height of the vessel, is lower. That is, the depth of the water is greater where the depth of the level is lower. So, this is water filling allocation. It basically translates into the fact that in the MIMO power allocation, more power is allocated to the stronger channels, less power is allocated to the weaker channels. Therefore, in this module we have comprehensively seen an example of SVD based MIMO transmission, in which we have considered a simple 3x3 MIMO wireless channel. We have looked at the singular value decomposition of this MIMO wireless channel, the post processing at the transmitter, the post processing at the receiver, the pre-processing or pre-coding at the transmitter, the diagonalization into the decoupled MIMO channels, spatial multiplexing, and then finally optimal power allocation. So, we will conclude this module here. Thank you very much.